You're misremembering. Okay. Let's do this one about the Groovy candies, the Groovy M&Ms. All right, so the first slide I left almost completely blank so that we could see, is this an example of Bernoulli trials? So, Mr. Frederick. Sure, you got it. Kiara, they're wanting you to go home whenever you wake up. That's what they said. They wanted to be released. Okay, so number one, what's the first thing I have to check for Bernoulli trials? Two outcomes, success and failure. What's a success in this example? What's a success? Now, what would be a success? I reach in the bag and I pull out what candy? Groovy candy. You might not agree. You might think that would be a failure, but that's a success here. What is going to be the failure? Non-groovy. Back here. Or regular is fine. Okay? So we just checked off the box for number one. Number two. Do we have a constant probability of success? We do. What is it, Ureth? It's the 30%, so P equals 0.3. We have a constant P. What's the third thing? Trials are independent. Now let's think about this. I've got a bag of M&Ms. Yes, bag of M&Ms. I reach in and I take out one and I'm like, oh man, it's not groovy. Does that mean the next one is independent? No. Exactly. There's a new denominator and that means our probabilities have changed. But remember I told you, as long as your sample, my bag, is less than 10% of all of the M&Ms that are made, we're okay. So is my small bag less than 10% of all the M&Ms that are made? Yes. Yes. So here, I would say these are not independent trials. All right? So I'm going to put an X here. Trials are not independent, but our small bag of M&Ms, our sample of M&Ms, is less than 10% of all the M&Ms that are made. Ooh, good question. It's much easier to do, like, if you're looking at a school, right? If you are doing a sampling of this school and your sample is 100 students, what's 100 times 10? 1,000, and there are not more than 1,000 students at Christ Rate Jesuit. Right? So really, if you're doing a sample at Christ Rate Jesuit, you want to stick around 50, because 50 is less than 10% of our 560 or something, whatever it is. Okay? Okay, is everybody good on this as Bernoulli? Okay, so now let's answer some questions based on this Bernoulli trial. Okay, what's the probability that the first speckled one is the fourth candy we get? So I pull one out, not groovy. I pull another one out, not groovy. A third one out, not groovy. The fourth one is groovy, okay? So I'm going to write down the probability that our first success, and I'm going to use X to represent when we get our first success, this random variable X, equal to what number? The fourth one. Very good, Ureth. Now, before I answer this, because you can answer this without doing this question, I want to ask myself, what kind of model is this? We just said it's Bernoulli, so I told you once you say it's Bernoulli, which one is it? Why geometric, Leslie? Exactly, perfect. So this is a geometric example. Well done. Okay, now the way I'm going to write it is I'm going to write failure, 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 right? So that's 3 failures in a row. And then finally, success. Now I know some of you already did this or might notice that my 0.7 is repeating with multiplication. So are you okay? Are you allowed to use 0.7 cubed? No. Yes. There's nothing wrong with that. It's the same thing. Okay? It's up to you how you want to write it. That makes it a little simpler. So take out your yellow calculator and type in 0.7 cubed times 0.3. What is that probability? I was going to ask Jarvis. 0.0129? 103. That I hear? Yeah. Okay. We're on the same page. All right. So we have about a 10% chance that our first groovy one will be the fourth one we pick out of the bag. Okay, how are we feeling? Everybody okay with geometric? That's geometric. Okay? Look at the next one. What's the probability that the first groovy one is the 10th one? This sure seems like the same problem, but instead of the fourth one, they're asking you what's the likelihood that it happens on the 10th one. So now, instead of having 0.7 cubed, I'm going to have 0.7 to the 9th power, because we have 9 failures in a row, right? Not groovy, 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 not groovy. Whew! That's 9. Times groovy. All right, what you got?
That's not right. That's not right.
0.0121.
Okay, go for it, Leslie. 0.012 is what I heard. Awesome. So that's about a 1% chance that that's going to happen. So is it likely that someone's going to buy this bag of M&Ms and it's going to take them their 10th one as the first one that's groovy? No, 1% is not very likely, right? 1% chance, not likely. So let me try to take your brain to the next step, okay? If you go to the next slide, and I'm just going to ignore this question for right now. Don't cross it out, but just ignore it. I want to look at this question, because my question is, we looked at what's the likelihood that the fourth one is their first one. Then we looked at what's the likelihood that the 10th one is their first one. So to me, the next obvious question is, well, stop asking that question. Just ask, how many M&Ms do I expect to take out of the bag until I get my first groovy one? All right? There's actually a formula for that. Yes, bro? We're using the geometric model. And if you look here, remember this from last chapter. This is the expected value, or the mean. And it says to do 1 over P. So let's do that. Exactly. P is 0.3 in this problem. So our expected value, or mean, or mu, is 1 over 0.3. So in your calculator, what is 1 divided by 0.3? I think Lily E got it. 3.3 repeating M&Ms. Right? We can't actually take out 3 1/3 M&Ms, right? We can't. So we're saying about 3, maybe 4. And if you don't have them by then I'm like, oh man. No, don't sue them. It's just you went past what I thought was going to happen. Okay? But that kind of, hopefully in your brain, solidifies why this number was so low for waiting until the 10th one. Because really we're expecting by the 3rd or the 4th one, they've got their first groovy one. Okay? Everybody good on the geometric example here? Okay, now watch this. Let's read this one. Right? Is this the same question though, Jarvis?
No.
What does this seem like? There's only one other model. It's the binomial, because this is asking how many successes, 2, right? 2 groovy ones out of how many M&Ms? 5. That is a binomial model. Okay? So in this case, I'm writing down my random variable is no longer how many until I get my first success. That's weighting, that's geometric, that's not what we're doing here. Now it's how many successes, which is 2. All right, so watch this. This is what students do every time. I'm going to do something on purpose, see if you catch it. Okay? If I have 2 successes, that means I'm going to have 0.3 squared. Do you agree? 2 successes, you don't agree? Right? Success is 0.3, there's 2 of them, so squared. So, hold on. I got 5 M&Ms, Travis. 2 of them are groovy. So I made 2 of them groovy.
Is this a trick question?
No. Okay? Times 3 of them are not groovy. So not groovy. There's 3 of them. Do you agree? Now, when you read that, though, this is read as the first 2 are groovy. But David's brain knows it doesn't say the first 2 have to be groovy. It just says any 2. So it could be the first and the last. Could be the last 2. I don't know. Yeah, but in that 5, there's 2 groovy. It could be the first. Yeah, I mean, if you pick a handful, I don't know. Whichever one touches your palm first, I don't know. Right? Ultimately, though, they're talking about an order of doing it one at a time. All right? So do you guys see how I left a space here? I left a space because there is a certain number of combinations of 2 groovy ones out of 5 total M&Ms. You ready for it? Oh, you're not ready for this. I love it. Okay? Take a look at this slide.
Wait, so what was the trick?
It's not a trick. I just left a space. We just did this here. Right? We're talking about the binomial model. You guys see this right here? Have you ever seen that before? N choose K. This one? You ever seen that? The choose function? Oh man, amazing day. This choose function is a way to calculate the number of combinations when you're looking at a binomial model. Okay? Because what David's brain realized, and hopefully all of our brains now, is that the order doesn't matter. It could be the first 2, the last 2, the middle 2, whatever, right? Just 2 of them got to be the groovy ones. So watch what I do for the work here. So you're going to write down 5, right? We have 5 M&Ms, and we're choosing how many to be groovy? 2. Okay? So the formula calls for your total number you're choosing, 5 factorial to be in the top. And we'll go over what factorial means if you've never seen that before. Okay? Over the number of M&Ms you're choosing to be groovy, which is 2 factorial in the bottom, times the difference of them, 5 minus 2 factorial in the bottom. Now, what's really nice, because many of you are looking at me like, what? What's really nice is that you never have to use this again. But I'm going to show you how you can do it by hand. Okay? Right now, I'm showing you. Okay, who knows what factorial means? No one knows what factorial means? Oh, watch this. So factorial means 5 times 4 times 3 times 2 times 1. So watch what 2 factorial means. It means 2 times 1. What's 5 minus 2? 3. So 3 factorial is 3 times 2 times 1. That's a factorial. So if I said 11 factorial, it's 11 times 10 times 9 times 8 times 7 times 6 times 5. That's what factorial means. Now, some of you, if you're lucky, you'll take a whole class on this stuff in college. A whole semester, just this. Yes. Okay, now, the reason I wrote it like this was, do you guys see in the numerator we have 3 times 2 times 1? And the denominator right below it, 3 times 2 times 1? So that's just 1. So really, it's this. So what's 5 times 4? 20. What's 2 times 1? So when you divide 20 and 2, you get 10. So how many different combinations are there of 2 groovy ones out of 5 total M&Ms? There are 10. And that's what you multiply it by. All right, so in your calculator, if you did 10 times all of that there, you'd get the answer. All right, open your Chromebook. Let's do it real quick. We're fine. You got lunch after this. You can go over. Hey, I'm dropping a lowest quiz grade, okay?
All right, let's stay here all the way.
No, that's not what I'm saying.
I drop a test.
Okay. Wow, now we're really haggling. Okay, I want you to go to Google, open a new tab, and type in Desmos binomial distribution. I put it up there at the top. Desmos binomial distribution. Desmos binomial distribution. Okay, has everyone typed it in? And you should pick the first one, the very first one. So hopefully when you pull it up, it looks like this. Did you guys get this? Yes? Excellent. Okay, so we're going to do this one in the calculator, or in the Desmos calculator. Okay, real quick, 30 seconds. How many total M&Ms are we looking at? 5. See where it says N? Change N to 5. Okay? Does everyone see P? What is our probability of success? 0.3. Change that to 0.3. What is our lowest number here that we're looking at for number of successes? Don't think so hard. How many successes? It's 2. We're looking for 2 successes, right? Yes? Is everybody good? Okay. Now, the upper, because we're looking for exactly 2 successes, just write as 2 again. So write the lower and upper is the same. We'll talk tomorrow about what you do when it's not equal to. All right? So you should get 0.3087. Can anyone in their calculator do this for me real quick? I want to confirm that that's also 0.309. Can I borrow your calculator since you're not using it? Thanks. So 10 times 0.3 squared times 0.7 cubed. Well, you got to make it cubed, Douglas. 0.3.
Yes, it's the same.
Is it the same, guys? It's the same! It's the same! Let's go! Oh, Edgar's not here for that moment. Maybe he'll watch it. All right, guys.
Bye, Edgar.
We'll talk more about this tomorrow.